All right. So today I wanted to talk about kind of rules, and we'll talk about interpretable models, which are models that are very easy to understand. And kind of a little background for this is I've always been interested in how kind of machine learning works and helps us understand what's going on in the world. About I think probably at this point, probably almost 2 years ago, I gave a talk at the St. Louis Data Science where we talked about explainability. And we talked about what are the tools you could use as a data scientist to help kind of unpack and take a look at your models to understand how they're working and kind of how to explain various predictions. Now, today I'm kind of hitting a very kind of a similar topic, but we're going to approach it a little bit differently by instead considering what type of models you're using to understand your problem. And if that doesn't make total sense, we'll explain it as we kind of walk through this. Now, as we're going, feel free to ask questions. We have a small enough group here, and I'll pause every once in a while, but I don't want this to be like a 60-minute lecture. I'd rather much more like to have it as a discussion. So feel free to chime in as you go through this. This is one of my first times presenting this material, so we'll see how it goes. And that's why if there's confusing points or you're like, hey, I'm lost, let me know. Now, as part of this, as part of kind of what I'm going to be talking about today, I do have a GitHub repo that has the code examples for everything I'm going to show. I'm not going to, I'll at times go over and show some code snippets, and we can look if there's questions. I can actually run some of the code live, but it's not required if you're following along the presentation, especially I'm sure some of you aren't ready to kind of run these things. So it's there. Like everything I've done is easily reproducible, but don't feel like you need to run that. I think you can get most of the impact of what I'm going to be talking about, even if you're not a data scientist, but you're maybe somebody that consumes or works with data science. I think there should be plenty that you should be able to get out of this as well. All right. And then Dan, if people want to ask questions in the chat, that's totally cool. But if you don't mind, like just letting me know if something appears in the chat, because I don't have that window open on my computer. Sound good?
I'll keep an eye.
All right, thanks. Okay, so let's walk through this. I'm going to talk a little bit about some big picture stuff around this idea of rules and interpretable models. And then we'll jump into kind of 4 different approaches at the end and kind of talk about some of the trade-offs of either of those approaches. And I think the goal is probably to go kind of, I don't know, 45 minutes or so, 45 minutes, hour. We'll kind of play it by ear and see how we're doing and how the conversation's flowing along those lines. All right. Is everyone with me then? Okay. All right. Since Dan's shaking his head, I'm going to depend on him for feedback. All right. So let's jump into kind of why we want kind of rules. You know, what's the point of kind of what we're here? And I start off with kind of the obligatory kind of, hey, we know AI is important and we should all be working on AI. And right, for this audience, I think that's pretty much a given. So let's kind of jump right past that. And I want us to think about kind of when we're doing data science, what are the influences we have? And when I look and I talk to data scientists, and when we talk about the modeling aspect, so this is where you're kind of turning that data science problem, taking that data, trying to understand how best to solve it, and coming out with a prediction. One of the big influences we see is Kaggle. And so Kaggle is a great platform for learning and getting an introduction to data science. For those of you not familiar with it, it's a place that has both kind of competitive problems as well as problems that are just, cooperative. You don't necessarily have to compete against others. You can try to just solve it. But they give you a data science problem, and your goal is to build the most accurate model to get the highest score. And especially for these, for example, Zillow years ago had $1 million prize where people were literally competing, and you can see how small the difference is between the top scores there, trying to figure out who could build the most accurate model. And so one of the kind of byproducts of Kaggle is a very heavy focus on making sure you improve your models around accuracy. And this is where we'll talk about, there's other trade-offs to consider in building models. But I think Kaggle And even for those folks that come out of academia, often really heavily also focus on accuracy. Often to get published, the biggest factor for getting your work published in academia is showing that you've improved your model in terms of accuracy over the existing state of the art. We see this kind of routinely where everybody's kind of just doing incremental improvements, and that's how you can get a conference paper. That's how you can get published. But again, it kind of puts a very heavy influence on building models that focus on accuracy. And I have one story I want to kind of tell about this and this is probably about 15 years ago. Netflix had a competition. I don't know how many people kind of here remember this, where they offered $1 million. And the idea was if you could build a better model that improved upon their existing model and beat out everybody else, that team would get $1 million. And this was one of the early kind of first data science competitions. It drew a ton of different interest out there. And if we look at kind of what happened during that is early on, there was a number of teams that started competing, and kind of after the first few weeks, and you can see here's the kind of the performance over time. The first few weeks of the competition, people were like trying different approaches, different feature engineering, different algorithms, and there was teams were kind of leapfrogging each other, and there was a steady advancement in terms of the overall performance in the competition. People were building more and more accurate models, but then they hit a point where things slowed down. Now, to get past this next plateau and up, what some people figured out is, well, what I can do is if I take my model, but I combine it with somebody else's model, this is what we call ensembling nowadays, I can actually get a better model. And ensembling is a very powerful strategy. And the winner of this kind of Netflix challenge actually built an ensemble of 107 other different models. So you can think about the complexity of that, not just one model, but 107. But this is, if your focus is on accuracy and just eking out that tiny bit of performance, it kind of drives you down towards this complexity to be able to eke out that last little bit of performance. And so this is one of the consequences is, yes, you can get something that are very accurate, but when you build these very complicated ensembles, they're often very difficult to implement. It takes a ton more engineering effort to build out 107 models versus one model and get that deployed around that. And so that's one of the side products of this. Another kind of consequence that I see all the time is complex models are also very difficult to explain because there's just a lot going on in them. And I will tell you my perspective from kind of working within enterprises with tabular data. Although you'll have people like Pedro, and every once in a while on Twitter, every couple of weeks, there'll be a kind of a thread along this lines of explainability or interpretability really don't matter. We should put that aside. The reality is if you don't understand what's going on in your model, it's hard for you to debug it. It's hard to convince somebody else to adopt your model. There's just been too many things that have gone wrong. And some folks have to work in regulated industries where you have to go through things like model risk, where you need to essentially convince a third party that your model is not doing anything weird or strange inside it. And again, you have to kind of explain what's going on inside it. And so these are kind of the two of the big drawbacks that I see with this heavily focus on accuracy, is that often you end up with these complex models. And so an alternative to that, and this is what I want to focus on today, is what I'm calling interpretable models. One of the big founders of all of these interpretable models and kind of somebody who's pushed on it, and if you look in the literature, you'll see, is Cynthia Rudin, who recently just won $1 million prize for her work around this. But what interpretable models will do is they're much easier to understand. They're designed for humans to be able to understand what's going on in them. And I think this is valuable because it'll help you better debug and understand what's going on in your model. It's not a black box anymore. These pieces that we talk about interpreting, you can actually then put in front of your stakeholders, as we'll show you. It's easier to get legal approval, model risk management, all of that. And then the last piece is these models are often much easier to deploy. Many of the interpretable models I'll show you, you can actually deploy directly within a database. You don't have to go out and get a GPU and a bunch of hardware to be able to use these models. And I think that's another very attractive component to these interpretable models, is that piece there. Okay, I'm going to stop here. Is everybody with me, or anybody kind of have any questions about kind of the overall direction we're going here so far? Okay. And I know there's a mixture of crowd of some people who have kind of developed machine learning models and some people that kind of aren't as comfortable. So please let me know if I'm kind of losing you, or if there's some complexity that I should be adding into the discussion. All right. So I want to kind of, before I jump into this, I want to give a little bit of caveats. Like today, I'm focusing on interpretable models and that model aspect and the model selection part of it. But to really get things that are truly interpretable, to get truly explainable, you have to think a little bit broader than just the model. You have to think about how you've set up the problem, what you've done for example, labeling the data, what you've done for feature selection, feature engineering, right? Dealing with things like multi-collinearity. And algorithm selection is just one part of this overall chain of things when you're talking about it. So although I'm going to focus on it, kind of interpretable models, I don't want us to forget there's a larger universe that model selection goes within that's just as important when we're actually trying to build out simple things that people can understand. And I think last time I talked, I gave an example about kind of linear models and how even kind of a linear model can be hard to understand if you have, for example, multi-collinearity, where you have features that are going the same direction as well. All right. Okay, so let's jump into it. The first step kind of when, the first step when I have like a modeling problem, I always like to start with a simple baseline. I want to get some idea of, if I just use some simple methods, how good of a performance I can get. And I can tell you stories of like people who have literally worked for like a year on a project that never ran a baseline model, that they spent a year, somebody else comes in and it's 2 hours, figures out that they can get like within 1 percentage point of what that person has been spending the last year doing. So always start with like a simple place, and then you can always figure out how much to improve upon that. I'm going to use what's called the adult data set, or the census income data set. It's a very popular data set. I like it because it has a mixture of numerical and categorical information. It's also a little bit meaty with 30,000 rows, has collinearity interaction effects that make it a bit interesting. And so I'm going to use that as my kind of starting point across all these data sets. And I like it because it represents a lot of enterprise tabular data, and all the examples that I have in the code kind of stem from that. So if you have other data sets that are numerical and categorical, you should be able to plug them right in to the code that I have as well. All right, so let's think about kind of, if we're working with this UCI adult data set, the objective of this is to predict income. So is somebody high income or low income? You can think about it. And it's got various information like demographics in there. And typically kind of, if you're working with a classification problem, your typical baseline models will be building a logistic regression, which is kind of the easiest, quickest way to go. Maybe using an AutoML baseline, that's what I'm going to do here, and then using 1R. And so I built these baselines, and I'm going to just kind of jump right to it and kind of show you the performance here. So at the bottom is AUC, which is a performance that's often used in classification models. 1 is the best, kind of 0.5 is the worst. It's basically random. And so we want our models to be as high as possible. You'll see that, the stacked ensemble here does the best at kind of 0.93. The logistic regression, where I use all the numerical and categorical features, comes in a little bit about kind of 0.91. And then I have the logistic regression, where I only use the numeric features. Doesn't do nearly as well. Like there's a big shift between going from numeric there. And then this 1R here, it gets like about 0.6. So a little bit better than random. It helps us make a decision. So sometimes a little bit better than random is great. Like if you're playing the stock market, if you're betting on football, right? A little bit better than random you can end up with making good money. Other problems, a little bit better than random isn't very good, not very useful. In this case, it's not very useful. But let me explain what 1R is if you're not familiar with it. It's a very simple model. It's a very simple model that that goes through all your features and just tries to see if I only had one feature, only one variable in the entire data set, how good of a predictive model could I build? So this example here is like on the iris data set where there's 3 possible outcomes. What if you run 1R, it finds out that, hey, if I take this feature of petal width and just divide it like this, I can actually classify 96% of the instances correctly just by using one feature. It's a great way to actually also detect if you have target leakage, if there's one feature that's kind of maybe cheating and shouldn't be in there in the data set. I mean, at the end of the day, if you can use one feature and get, pretty good predictions, why, might as well just stop there instead of keep on going for a lot of problems. Okay, so that was, in case you weren't familiar, there's a number of different implementations of 1R. It's a very simple, I almost wish like everybody would just include it as like an easy out of the box baseline around that. And then for kind of the best model, I ran kind of a standard AutoML model. I just ran the H2O AutoML kind of stacked ensemble, which consists of like 20 models of like, I don't know, like neural networks and gradient boosted machines all put together. And that gives me a good idea for like, hey, what's the max I could get if I threw all the different best algorithms at this? And so what we're going to do is now kind of work within this range. Any questions here on kind of baseline models and kind of the starting point where we've got so far?
Yeah. So I wanted to ask you, I was curious about what,
yes.
How do you measure the complexity in this
chart
that you're seeing here?
Yeah, so complexity is a bit of a made up number that I have, okay? I'm also working on a blog post and I explain that, but yes. So what I've done for complexity here is it's essentially basically like the number of features or parameters for this model. So for example, for the logistic regression with all the features, there's about 100 predictors that go into that. So I gave that a complexity of 100, while the 1R that has one feature going in, I gave it a complexity of 1. Does that make sense?
Yeah, it does.
The stacked ensemble should be way higher, but like I had to stop my graph someplace because it literally consists of 20 models with, and 20 models, and each of that has like, 15 features, and then there's categoricals that could blow out. So it's literally like tens of thousands of decision points, but I had to like I had to make an end somewhere. But all right. Okay. So first, let's start with Rulefit. Rulefit was one that I've been very familiar with. I've used for many years because it's one of the models inside kind of Data Robots product. What it does is with the Rulefit is it builds a number of simple kind of okay, let me step back. So what it does is it uses decision trees and very small, short, stumpy decision trees to build simple rules that help us kind of figure out and make predictions. So for example, it might say, if X5 is less than 7 and X2 is less than 3, then you end up in this category, which could, let's say, be low income, versus this category could be high income, where if X2 is less than 3 and X5 is greater than X7. So these kinds of rules like that, and this comes out of some of the early work around decision trees, where people noticed, like, if you just keep these decision trees really, really short, it's very easy for people to explain them. So H2O has an implementation of this Rulefit. And so I ran that.
Rajiv, quick question. We have a question in the chat about decision trees and how what you had there compares to decision trees.
So for me, this is, I'm going to say with a simple example, this is essentially kind of a decision tree, because what you're doing in a decision tree is making, I don't know, kind of, let me say one of a simple way, kind of you're making a decision at each kind of node here, and you're going to split into one of two directions. So it's either this or this, either this or this. And modern decision trees like random forest and gradient boosted machines are just built of huge sums of these and huge ensembles of these as well. Does that help explain things, or is the person asking happy with that? Or
Yes.
Okay.
We have another question.
Yeah.
Around what H2O is.
Oh, I'm sorry. So I just assume everybody knows all the providers in data science land. So H2O sells enterprise AI software, but they also have an open source product available, which you can anybody can download. It works in both Python and R and allows people to build machine learning models. I have an example of kind of their GUI open right over here, which is kind of their H2O flow product, which, for example, I can see here where I've built this Rulefit model. I kind of built that earlier, and I can go in here, and if I wanted to, this is using the GUI. There's a full kind of command line thing, but it's easier for you to probably understand it this way. See, what were the parameters I used in this model? Here's the names of all the features that were available in the model. And then I can see what are the outputs. I put my data in H2O, it outputted the model. And so in this case, we're building that Rulefit model. And what's going to happen here is you'll see that there's a number of different kind of rules that pop up. And let me go back to the slide to kind of walk through and explain one or two of the rules here. So these rules are cumulative, where what we want to do is for a given prediction or a given example, we'll examine and see which of the rules apply to us. And then in that case, we'll kind of sum up the coefficients, which will then be able to turn into a prediction. Now, the rules are a little bit complicated to read. This is in kind of computerese. And so if you were going to, show these to end users, you might want to simplify this. But if we look at this top rule here, we can see, what is it? If education is kind of less than 12. So, if somebody has less than kind of a 12th grade education, for example, and if we look at the relationship here, and the relationship is they're not in the family, another relative, not married, and their capital gain. So how much capital gain taxes, their capital gain they've declared the last taxes, and this is data that's like 20 years old, is less than $7,000. All of these lend to a powerfully negative coefficient, which actually in this case means they're very likely to have a low income. And so this is what we would consider one rule. This is kind of a 5-rule tree where I've built 5 different rules, and you'll see each of these have different coefficients. And I can use this to help identify kind of certain rules or segments of my data that, for example, might be very likely to be poor or very likely to have high income. This is a model I've used. I used it often, for example, with like predictive maintenance, where I would look for rules that would lead to kind of that were like highly predictive of a failure, for example. And that was very successful in finding like faulty part systems, for example. All right, are people with me so far kind of on these rules?
Yeah. One point of clarification, just so I don't get lost. So typically when this is a binary classification problem, right?
Yes.
And so what's your positive class? Is being poor or not being poor?
So the positive class in this case is high income.
Oh, high income. Okay, good. So therefore, a negative coefficient would be pushing the decision towards negative, right?
Yes.
Okay, good.
Now, in this case, if you look at this model has like a 0.8 AUC, which really isn't that good. And so, you might think like, hey, what am I going to do about this? And I think that's one problem with that. The other thing is I want people to remember is the rules here. Remember, we had 5 different rules, but they can overlap. So one person could be affected by multiple rules. And this might affect us when we start thinking about interpretability, because now we have to keep track of multiple rules for a given prediction. It's not the end of the world. It's just something to consider like that. Now, one of the reasons I like the H2O approach is the previous thing, all the decision rules I had were those decision trees where I had to break things into small if-then buckets. Now, if I have something that's a continuous feature, so if you think about like how many miles you drive for the likelihood of an accident, we know the more miles you drive, the higher likelihood of an accident. If I'm using this approach here, sorry, I want to go backwards. I'm not going backwards. Okay. Let me go back. If I'm using this approach with what we'd call a continuous variable, we end up having to what's called bin that or break that continuous variable up into segments. And that's one of the downsides of using a rule fit when you have those continuous features. The nice thing is the H2O implementation supports both the decision trees, but also supports having linear relationships as well. So you can see here, for example, there's a coefficient to education number, which means like every unit of education goes up, that affects that coefficient in that same amount. And so in that way, the model is able to capture those types of linear relationships in your model. And this is kind of important when we start talking about these interpretable models, because some relationships are very continuous and that linear captures that dynamic better. Right? Some things are, what's the opposite of like categorical, or they're, I don't know, easily binned, and kind of the rules will capture those types of things. And so it depends. Now, the example I have here is on that adult data set. Like your problem might be very different. And that's why it's important to kind of run some of those baselines and get an idea of kind of what signal you're seeing in your data to see what approach works the best. But this is one of my favorite things, is that H2O, because you can bring in the linear, you can actually build pretty accurate models. And here's kind of, by adding more and more rules, of course that gets complex and you have to think about it, but you can actually get accuracy that's pretty close to that ensemble that I showed earlier with kind of the AutoML that had tons of parameters like that. And it's simply a matter of just deciding how high you want to turn it. Now, you're not going to get everything because the rules in the rule fit are still short, right? They're only simply kind of 2 or 3 levels deep. They're not going to be as deep as some approaches, like an XGBoost model that might be able to catch some really fine-grained complexity. So you're probably never going to get, for every data set, you're not always going to win with rule fit, but for a lot of them, you can do pretty good by just affecting that the number of rules. All right. Is everyone with me so far? So that's the rule fit.
Raj, yeah. I have a couple of questions, and you can address them now or later. So the first one is kind of a follow-up of what you mentioned of the relationship between the accuracy of the model and what you can do with it. So I wanted to know your stance in general. Like, do you want to have first a very accurate model to then do the interpretability, or what do you do with something that is kind of but allows you to do some interpretability, and what is the level of credibility of that interpretability if the accuracy is not good? So that's the first one. The second one is that if you take a look at the rule fit with the rule fit with 200 rules, not only the number of rules is large, but the number of variables is large. So you might be drowning there in different combinations of rules. It might be a little bit of a challenge to come up with something that makes sense to people, like in marketing or something.
Yeah. So those are all fair points. And one of the things is there's always going to be this trade-off of how easy something is to explain and how much performance you're getting out of it. Because unfortunately, there's just not a lot of cases where something is simple to explain and gets you max performance. Usually there's some types of complexity in there where if you figure out that complexity, you get the boost and improvement. And kind of where that trade-off is depends on your use case. Now, one thing I will say, even the rule fit, even with 200 rules, one of the advantages of that is those rules are very simple. It's if this happens and this happens, then assign it this coefficient. So you can take that model and put that into a database. You can kind of write that model out very simply in literally like simple Python code that anyone can understand and run, versus kind of that XGBoost model where you're not able to, like in the same way, really understand what's going on inside all those trees. Does that help?
Yeah, it does, but then it makes me think of, in the case of XGBoost, of things like Shah. I don't know if you want to.
So, so one thing to point out here, there's two different approaches. One, and that's what I talked about last time, is taking a complex model, using tools to help understand what's going on. What we're doing here is starting with a very easy to understand model, an interpretable model, and building there. Now, you're right, as we add more and more layers, it might get more complex, but it's still kind of at its core, something that you can open up and read versus having to bring in other tools like Shapley explanations to take apart a complex model. Okay.
We have another question in the chat about how you deal with overfitting in Rulefit.
So the overfitting in Rulefit would really be just like any other type of algorithm that you would deal with. So you would kind of follow your usual practices of having, a separate holdout set that you would be testing and evaluating the performance on to kind of make sure you don't fit, because really the Rulefit is just going to have the same issues of if you were building a random forest, for example, like that. Does that make sense?
Yeah, I think that they're probably satisfied.
Okay. All right. So let's move on to, I got a bunch of approaches. And so let's go on to the kind of GA2Ms. These are kind of the GAM models. They were introduced kind of about 10 years ago in a paper, and really almost nobody kind of picked them up, or they were very rarely used. When I worked at DataRobot implemented them. And so I got quite familiar with them over the last 3 or 4 years. Recently, Microsoft has implemented, and it's actually Karuna, who's Microsoft Research hired him, has actually taken and made an implementation of what they call explainable boosting machines, EBMs, which is basically these GA2Ms, is available now in the Interpretable. So now there's an open source implementation that anybody can use. Now, what the GA2Ms are kind of very related to GAMs, and for some of you might even just think of them like kind of a logistic regression model, where what we're going to do is instead of, there's a couple of differences between the GAM2 and what you'd see in a classic regression model. One is for numerical features, we're going to bin those numerical features. So we're not just going to have one coefficient for a continuous numerical feature, but as you can see here for like criminal, we're splitting it up between the values here, between minus infinity to 0.3, there's a coefficient. Between 0.03 to 0.6, there's a coefficient. So it's a little finer tuning of those continuous features. The other big advancement with the GA2M, and this is where the 2 in GA2M is it brings interactions into play. So one of the reasons decision trees often did so well is that you could kind of interact 2 features together kind of at once. And the GA2M does that by being able to, for example, take the interaction between, in this case, crim and lstat, and give that coefficient. And so it's a very transparent model if you're used to things like logistic regression, where you could see the coefficients of not only all the features, but also your interactions. And the big kind of advancement it made is everybody knew interactions were useful. I mean, people have been using interactions forever with linear models, but when you get a large set of features, it's hard to figure out which of the interactions you want to keep in your model, because you can pair every feature with every other feature. And you could sit there all day long if you have 100 features trying all the different combinations. And so there's an efficient algorithm within the GA2M to identify which are the strongest interactions, and it uses those. And kind of once I ran this one on this data set, I was able to kind of get kind of a 0.93 AUC. So similar performance to that stacked ensemble model. So the EBMs or GA2Ms work really well. Now, of course, for some types of data, they might not work that well, but it's an easy model that gets you really good performance if you're willing to kind of have kind of similar coefficients that you would get. Here's the Interpretable page. You can go check it out. I don't know. I don't know what else to say. It's easy to follow. They have plenty of information on it. But like I said, what you get at the end of the day is, and they have like, I can even show you in the browser here. The Interpretable even has a few nice visualizations that go along with it so here's that code book that I have for kind of building it. You'll see one of the things is when it builds here, it also tells you which of those interaction features it's creating, and even comes with some visualizations where you can, for example, go in and if I want to look at some of these interactions, I can look at the interactions between these features as well. Can't remember which ones were interesting to look at, but or you can just, here's, for example, is occupation, and I can see, what effects different occupation had on there. So kind of, in this case, it's your traditional coefficients you'd kind of see for that. But I like to think of this, right, as it's an easy step kind of beyond your logistic regression that picks up a little bit more signal like that. And because it's very close where people are used to seeing these kind of coefficients, model risk teams, places that have that or that are used to traditional logistic regression models are quite accepting of this approach as well. Have people heard of this? Is this kind of new for those folks that are in modeling, or?
New to me.
I think it's fairly new, yeah.
Yeah.
I've used it before, but so the challenge here is that you have a score, right? And then how do you communicate that to the end users? And you say, well, this has a larger score than the other, and you go, okay, and what does that mean for me?
Exactly, right? Like when you, no, it's a very fair point. Like these coefficients, like if you're a data scientist, okay, like you've been trained to learn how to understand and what coefficients are. But if you're showing that to your marketing department, they're going to probably be like, you're going to have to give us, right? Because the coefficients don't even translate directly into probability. And it gets really complex to kind of explain that to somebody, except like, the bigger the coefficient, the bigger it's going to move it. So, you're absolutely right. Like if you're trying to talk to this to an end person, especially because of how many bins get created, because you can think if your numerics are all getting binned, you have a separate level for every categorical, like there's a huge list of coefficients that somebody's going to have to look at. And it's a little overwhelming then when you get one prediction to figure out all that stuff. Oh, good.
Would you say that it also, depends largely on how good it translates into what they understand in the business? That if what you're getting out of the interpretation of the model actually makes business sense, do you think that it's a little easier to communicate?
It might be a little bit easier, but it's still right. Like I think coefficients it feels like people are going to math class. If you do that to kind of a regular audience, and this is where we talked about kind of earlier that model is just one part of it. This is where if, for example, you have a ton of multicollinearity in your model and you're trying to explain into marketing, like how one indicator has positive coefficients, another one has negative, and they're like, well, shouldn't both those go the same way? They're both related. Like you can get into trouble. So this is where, if you do your homework on the feature selection, all those things upstream, then maybe, you can have a simple model with coefficients to explain.
Yeah.
But I think go ahead.
I was going to say there's also a question in chat. They said, how do you deal with correlated variables with this model? But I think they're thinking of collinearity. So maybe you could.
Yeah.
There.
Yeah. So if you have, for example, good. So if you have multicollinearity, right? So you have features that move in the same direction. So you can think of, if you're working with children in height and weight, as height goes up, weight often goes up at the same time, is often a common problem. And the reality is most kind of modern machine learning techniques can handle that fine with techniques like regularization, for example, with linear models or kind of decision trees, because of the way they split and bin things off, can kind of deal with that multicollinearity without it being that big of a deal. Now, that multicollinearity often doesn't affect the accuracy of the model. Like the predictions will come out very accurate, even if you have multicollinearity. It's just the explanations can get really crazy. because one feature is going up, one feature is going down, and kind of explaining that can get a bit messy. Does that help? Yeah. Okay. But we have some solutions. I got some other techniques that can help us through kind of this issue of coefficients. The nice thing again here is like through model risk management, through if you have to implement this in kind of a database or through some other way, it's very easy because, hey, I'm just binning this thing. Here's the coefficients. I'm binning this. Here's the coefficient. So you can code it out very easily. All right. So let's talk about kind of a different approach. And this is what we call, or what's called rule lists. And when we talked about the rule fit, remember the rules were overlapping each other. Somebody could be affected by two rules. Instead, what rule lists do is they limit it so every individual observation or prediction is only affected by one rule. And so this makes it much simpler to be able to understand what's going on. Now, to do this, and I've listed a couple of different implementations here. To do this approach is takes a lot more computation because you have to kind of take a look at the data and slowly kind of figure out what is the best set of rules that covers the entire data. And one of the problems with kind of the rule list approach is that as you try to get more complex sets of rules or deeper sets of rules, the amount of permutations blows up and it becomes hard to kind of calculate these things out. So it works well for simpler rule sets, but it still takes a bit of computation. And so what you get is this is that same adults data set, but this is as a rule list. And so the idea here is what somebody would do is you basically start with your prediction, like the person has a certain education, capital gain, and you just go down the list until you find the rule, and then you get the score. So for those computer people, it's basically like a if-else if. It's written here, I guess, like that. And you just keep going down the list until you find the rule that applies to you. And these lists have been built so that it'll cover the entire types of all the possible predictions with some type of result. So you'll see in this case, right, if the capital gain is more than $7,500, the first thing it's going to do is just say, hey, if it's between, $7,500 and I think that's 10,000, that's going to be a high income. But if it doesn't fall within that range and the education is between kind of 1 to 4, right? Like almost no education. Instead, we're going to say that probability is low income. And so you walk your way down this. And so this is right much easier to explain to those marketing people. Like there's a bit of rules there, but everybody ends up with kind of one rule. You also you're not like adding numbers together or anything like that. Like you just get one rule. Like you might have to go down a couple steps to figure out what rule it is, but that's how this works. So some implementations of this you'll see is there's an iModels package that's out there that I should kind of highlight that has a bunch of these interpretable models that I've been talking about. This Coral's certifiable optimal rule list is a very popular implementation in Python for this. I just had trouble getting it to work. I couldn't get it to work very well. It would just kind of blow up on me. I went back and followed, there's SBRL, which is Scalable Bayesian Rule Lists, which Cynthia Rudin, kind of her team wrote, and it runs in R. It's like an older R package from like 4 years ago, so it was a pain to install, but I was able to install it and kind of get it running. And literally like on that adult data set, I was able to build this set in about 30 seconds, which is pretty fast for that. All right, is this rule list a little bit easier? Does this make a bit more sense? Now, the trade-off is, of course, is the accuracy, right? We don't get the same type of accuracy where with Rulefit and the GA2s, we were able to get pretty close to the top model. Like here, we've definitely kind of lost a little bit in terms of accuracy, partly because if we think about those linear continuous features, it's much harder to capture these when you're doing kind of this binning process like that. Okay. I'm going to take the silence as okay, and I'm going to keep going if everyone's all right with that. All right. Okay, so this is the last approach, and it actually kind of gives you probably the simplest and the easiest for kind of people to understand. And these are what's called the scorecards. And scorecards are widely used in kind of various domains, like I think like within criminal justice, within healthcare. I think even sometimes within credit scoring, you'll have these very simple models where you'll just list a couple of features, maybe areas of the feature, and we just assign points for them. And the way the model works is you just add up the points, and then based on the score, it's in this case one category or not in another category. So kind of when we're talking about like the simplest models for people to understand, I think the scorecards are probably kind of right there at that. Okay. Now, calculating these, again, can be computationally challenging. There's kind of, I use the opt binning, which actually works pretty good, which is close. I think it just works off the logistic regression. There's also some other ones like the sparse linear method, SLIM out there that you'll be able to see that build out these scorecards as well. So when I built out the scorecard for that adult data set, oh, I didn't put the AUC for this. This is what it kind of looks like. And you remember that adult data set here. This is 15 features. I didn't try to do any feature selection. So a few of the features dropped out of these. And then many of these features had lots of categories as well. But I think in contrast to like those coefficients that we showed earlier, this is something that might be a little bit easier for somebody to stomach and palate, where literally you just go and take your example and see how many points there are for each feature, and then just sum up the number of features points, and that what tells you high and low. I actually like this better than the coefficients because I think it's a little easier to understand, for example, which features are most important. Like you'll see like capital gain here, like 29 points. Like you realize that, hey, if somebody has a high capital gain, man, that's a huge predictor. That's a hugely impact factor for that they're going to be high income, or that if the age is less than 25, they're probably going to be low income because of that, or kind of right the effect of being married versus not being married here. And so I think but the GAM2s will win out in terms of the model performance because they have so many coefficients. But if you're willing to simplify down the coefficients, I like this method for giving people something much easier to understand as well.
There's a question in the chat about how these points are used to make a categorical decision.
Mm-hmm. So, yeah, and you could. So when I built this model, I kind of set a max and min. Let me see if I can pull up the R code for it. Or no, this was the Python model. Let's see if I can find that. So this is my little scorecard model here. And this is essentially what I did is it's kind of ran an estimator on a logistic regression. And then I just set the scoring parameters between 0 and 100. And so in this, I picked, if you were doing like credit scoring, maybe you do 300 to 800 because that's what credit scores are. I picked 0 to 100. It's almost analogous in some way to like a probability. So as the data scientist, you could figure out, well, here's the score range of scores. You could even plot the scores and then figure out what the threshold would be that you would want to say, hey, in this case, this is what's going to count as high income or what's going to count as low income. So depending on how you're going to do it. I was able to kind of use those scores and get the predictions and then just still run it through kind of a typical, being able to kind of plot out the AUC and all that kind of stuff as well, and rock curve, just using the scores. I know, yeah, you can see here, it's 0.89, so it's better than that kind of rule list model performance, but it's still a little bit shy of like the 0.92, 0.93 of the best models that we have out there. But yeah, the scorecard, yeah, it works really quick, easy. You can kind of adjust a lot of these things like that. And it's just basically creating these bins, and then you can just set how much rounding you want to do. Do you want to, in this case, I rounded it off to make it look much simpler because I just wanted nice integers instead of decimal points. But if you want it. And again, like if you have to implement this, this is super easy to implement. Like you can implement this in a database for doing this. So think about like if you need like super high scoring models or super quick scoring models, this would be easier to do.
Hey, Rajiv.
Yeah.
So if you're setting the score, you would have to kind of know the upper bound, or if you're setting the score range, you would kind of have to know the upper bound then, right? So like if you were trying to predict a person's income, you'd have to set the range somewhere.
So let me be clear. So what this is doing is this was based on a logistic regression, a classification problem. So the classification problem is one of two categories. And then the score is just going to basically be some type of number that's going to go between the lowest probability to the highest probability. So you can vary it between 0 and 100 or whatever else. So, and partly because things like credit scores, people are used to between 300 to 800, or right, you might have some other card where you're like, you know, have some arbitrary scoring thing that you want to start with. So there's a whole science into itself of like creating these scorecards and literature around all that stuff. Okay, so this is like, if I try to like graph out all those approaches like we talked about, here's kind of how they all kind of do it. And of course, again, the stacked ensemble is the best, but you know, the Rulefit, if you add the complexity, you can get pretty close. You know, the GA2Ms get pretty close in there. The rule list and scorecard, right? You lose a little bit compared to, let's say, like the logistic regression model, but right, we talked about the trade-offs of being able to easily understand kind of what the coefficients of the factors are, or maybe on the other hand, like with the rule lists, just having one simple rule that explains why you're getting your score instead of having to like sum up a bunch of categories or something and do some math. All right. So to kind of wrap this up, you know, hey, try these approaches. I mean, I know some of you kind of run things like XGBoost or neural networks all the time. As you're doing it, it's, I think, some of the questions we talked about, you know, today that you have to kind of think about, like, is this about making it transparent, how it was calculated? Is that the concern, that you want to kind of make it easy to see exactly how you came to the prediction, where maybe you want to expose those coefficients? Or is it about making it easy to understand the prediction, be able to explain to somebody exactly what factors led to the model giving them a certain prediction or a certain score? So this is where that scorecard, for example, in a healthcare criminal justice context comes into play. So yeah, take some time, add them to the modeling toolkit. If you really kind of are all about this topic, let me know. I have like a blog post coming up, and I'm always happy to look for people to read it ahead of time and give me feedback on this. But basically, it's just a blog post taking together of what I put all this, what I covered today, basically, and trying to get into one post around that.
Yeah,
all right. Yeah.
Quick question. Kind of maybe slightly different from what you've just covered here, but are there methods by which we can force the model to incorporate certain rules? Like, for example, you know, in the credit risk kind of scenario, can we force the model to, you know, incorporate a rule which says anyone less than, like, say, a credit score of 600, don't give them a loan?
So there's a couple of ways to kind of handle that problem. Generally, the way most machine learning models work is they leave it to kind of their model metrics, or the kind of the optimization metrics built in them, to hunt around and find the pattern within there. And so kind of it's hard to kind of make the model do something that it doesn't want to do, because usually you just point it in the direction you want to by some sort of optimization metric where you're saying, you know, give me the least error. And it's right. The beautiful part of the model is that it figures out from all the features that you give it, like what's the best way to get to the least error. So one way to incorporate, like if you have some type of constraint like that, is to try to think about bringing that into that optimization metric So when it's reducing the error, it takes that into account. So that's one way you can do it. Another way is doing it on the pre or post processing side. So a lot of times what happens is models will produce output, but the outputs they will produce will then go through post processing, where there's some regimes where, for example, if the credit score was below, if the model gives a credit score above 800, and we know that, well, like, there shouldn't really be a credit score after 800, that could easily be rounded down to 800, or that might be a sign that something has gone crazy with the model, and we might push that and say, hey, somebody go manually check this prediction. So, there's all types of processes we can have kind of based on those model scores to take into account different behavior to account for some of those. And so that's where a lot of places will just kind of, instead of trying to force the model to find that, we'll instead deal with that on the post-processing side. Does that make sense?
Yeah. Thanks.
Yeah.
Another way would be to try to pose some sort of a constraint optimization problem, right?
Yeah, and it just gets a little more complicated because then you're messing with that optimization metric inside there for kind of how it's trying to find its way through there.
So Raj, I was wondering if I've never used Scorecard, and it sounds really interesting. Now, I was wondering, can you use it in regression problems instead of classification problems?
So generally, what I've seen for the scorecards, and again, there's like a number of packages, and there probably is some R package out there that has made something like that for a regression package. I haven't, in my quick perusal, I didn't see them. I will kind of tell you, I'm much more familiar with the GA2s and the Rulefits. I mean, the scorecard and the rule list were things that I've spent a lot of time learning about this last month or so as I was putting this together. But I see no reason why you couldn't kind of build something along those lines. I think the hard part is just kind of going through that optimization to figure out how to kind of build that scoring part in. And it's just easier to build the optimization that a lot of these things go through when there's specific bins. So I think it's just partly the complexity of the problem gets a little harder for that. But if you could think about taking a regression problem and just bidding it, then it would be a very easy way to do it.
Yeah, the complexity that I kind of anticipate is how to explain the score, right?
Yeah. Well, I mean, you mean if the
target is something like, I don't know, sales.
Yeah.
Right. Does it mean like that the score is kind of a contribution of that variable to the actual target? And if it is that a general interpretation, or is it a local interpretation? Right?
Yeah. Yeah, I don't know. I mean, I guess you could do like high sales, low sales, but you're right. As I don't. I mean, I would just generally assume like the more points, the higher the sales.
Well, that's exactly, yeah. So I would need to make the connections so people, people have something useful.
Yeah. No, I think this is much easier for like a classification.
Correct. Yeah.
Kind of probability kind of thing than that. But you can see, like, right, if you could, this is something that's very easy to give to an end user because you could literally like put it on like a little card and tell people, hey, this is how we evaluate, and everybody can kind of see.
People love this.
Well,
people love put stuff in bins, right?
Yeah, I mean, because I think there was a recent case of, I think it was with like, it was one of the medical centers. I don't know if it was like in San Francisco or Stanford or something, where they had a algorithm to identify which people should get the COVID vaccination or not. And the algorithm itself, right? Somebody, I don't know if it was logistic regression or what, but there was really complaints that it wasn't clear exactly how the algorithm was choosing whether or not you got tested. And you could see, like, if you knew that you were going to have something that was high stakes and a lot of people were going to look at, where you had to get that confidence, giving people out and telling people plainly, like, hey, this is the criteria we decided to use for who's going to get the test and who's not going to get the test, makes it much easier than trying to a machine learning algorithm that might improve your AUC or your little performance by 1 or 2%, but the more important thing might be the ease of communication and transparency versus kind of getting one or two of those people in the right category.
Yep.
All right.
I was going to ask one thing, and it's a little bit technical, but last time we heard from you, I believe you cited Kleinberg and his paper on the relationship of interpretability and fairness.
Yeah.
And I remember that being kind of the strong point of the case of using these more complex models and then interpreting them later. And it seems like you went through a little bit of a transformation in the thinking based on what you were just saying. And I'm interested in that because I do think that it does make sense that impact is really maybe what matters the most. But maybe you could speak to that, like what I'm talking about, or like why fairness matters, and how this would play out in comparison to like a more complex model that might have a little higher utility and be able to make slightly better decisions for somebody or benefit somebody versus what you're doing now.
Yeah. And I mean, so I think the Kleinberg is one where kind of he pointed out that maybe complex models could be fair because maybe the complex models are picking up on elements of what's going on in the world that us humans, that we can only take into account a handful of features. And maybe there's some features that are going on that actually a model to predict whether someone should get bail or not, because the computer can take into account so many more features. Maybe it's actually fair because it's just kind of smarter by taking into account all that information.
Yeah, I think that's what he's saying.
Yeah. And I think the problem is the jury is I don't know if the jury, it's hard finding good examples of that. It's much easier finding good examples of where the data is crap going into the model. And yes, it has 20 or 100 more features, but we know those features are very biased, and that if anything, it's hurting the model and what it's thinking more so than that. And this is where kind of this complexity argument, right, that kind of Pedro and others make, kind of falls apart, because the reality is you can't think of a lot of fields where the people say, oh, it's too complex, I'm not going to be able to explain to you, you have to trust me. Now, they might say that to a layperson, but within the doctors, within themselves, within the engineers themselves, they still have to communicate to their peers exactly what the process is and how it's going. So, I mean, in that same way, that's where I think kind of our models are held to that same standard. Like if people can't explain and understand, and I'm not saying that you have to explain that model to, just somebody off the street, but if you can't explain what's going on, in your sales forecasting model to the other people working supply chain and prices, and those factors there, they don't see like, oh yeah, that makes sense why the model's doing this and this and this, and they don't understand the relationships. There's, you're probably, it's going to be hard for anybody to gain confidence on that. And we've seen time and time again, we've been burned by models that pretend to be complex, that pretend to catch these scenarios and then fail in the real world to actually capture things, or right, the world changes a little bit and they fall apart dramatically.
Yeah, I think I think that's a really good summary, and definitely, corresponds with my experience in applying these kinds of models. And so, and I definitely think that it's just, it's easier to get buy-in, which in the end, I mean, even if that complex model is really great, and nobody wants to use it, then how great of an impact can it really have if nobody trusts it? So.
Exactly. Yeah. I mean, and that's the biggest reason I've kind of pushed back towards these kind of interpretable models, is simply because it's easier to get your subject matter experts to kind of nod their head and kind of agree with what's going on. And a lot of times it's better to just get a model that's, doing pretty good, that you can get in and get into production, instead of waiting 6 months or a year to convince everybody else to, gain that extra % of accuracy. And there's also other ongoing issues of things like data drift and analyzing the model after it plays into play, where, these models that are simple to understand, if something changes in the world, it's a lot easier to see how it's affecting this model and think about, should I retrain what I should do, than if you have like a complicated, more of a black box model where you're not exactly sure what the interactions are when, the price of gas changes and what's going to happen to your model.
Yeah. Well, with that said, though, do you think that there's still going to be a place moving forward for the more complex models in decision making, or like when would you draw the line?
I mean, I think a lot of it comes down to that business of like where that performance matters. For some problems, going from 0.89 to 0.93 AUC, it's not going to matter that much to the business. But for other problems, it could be worth, millions or billions of dollars. And depending on the consequences of that, yeah, I mean, I think, for example, I think click-through ads, that the models that Google and other people use to figure out what ads to show you, right? Those things are like hundreds of an AUC, like they get, moved up and, decided on that. And so for them, even that tiny bit of improvement has dramatic kind of revenue things, and those will go up. But I think there's plenty of other models that don't need that level, where the world, they're not doing anything now. Even if they just get a simple model into place, it's going to make a big difference.
So you would say maybe that the real baseline is what we're doing now and how well it's working.
Absolutely. I mean, I think all these data science problems, it's important to kind of step back and remember the business context and the overall context for when you're kind of doing these, when you're setting up the problems and thinking about the implementation and what the baseline is. Like, what is good enough for this model? I mean, for some, it might have a very high baseline. For some, for some problems, whether you get between a 0.7 to 0.8 AUC really doesn't matter to the business. As long as you get something there, that's good enough. And I think, yeah, having those discussions early on, so that way how much time your data science team should spend, is kind of important. Because, yeah, data scientists often love to do the modeling, and they'll just spend forever, incrementally improving it. And if you let them, they'll spend an extra 2 or 3 months eking out a tiny bit of performance that nobody else cares about, like that. So, yeah. All right.
I have to ask, do you have any comments on Zillow while you have the stage?
So, I mean, I like Zillow. I mean, I know Jordan, he won the Zillow competition, and he was a data robot when he won, and then he moved over to Zillow. And I know kind of how good of a data scientist he is. And I think that's a case where, even though your model might have perfect predictions, there's a whole difference between kind of forecasting something versus the business being able to use that number. And especially in the case of Zillow, where you kind of tell both the people that are on your side and the people against you what that number is, because then they can kind of use it strategically against you, right? If you know your Z estimate is way high, or I don't know if it'd be way high or way low, like you can, then act accordingly to that information, which kind of can give you an advantage in ways, and kind of selectively pick your transactions. So, no, I mean, I think it's a great example of, like, even though you can build a really good prediction, like the world of business and how you use this stuff is pretty raw. I mean, I think financial services has seen it forever in terms of predicting market activity and stuff. So, yeah. And yeah, I don't know. Anybody else have thoughts on that? So, I mean, those Zillow people had very complex models. I mean, they had like terabytes of data and fancy neural networks. And like, I'll tell you, like Jordan, who did it, it's not like he was just a data scientist that just all he knew was math. Like, the guy understood real estate too. I mean, he understood, like, the difference between houses on kind of lakefronts versus on lakefronts on the water, and knew kind of all this fine demarcation in terms of how to do this. So he had a lot of domain knowledge. It wasn't just like computer science like that.
Yeah, I definitely think it's interesting that you bring up the dynamics of the real world, and the fact that models are actually happening in real life. And, that if somebody can see your hand, that's a lot different, and that's going to, it's going to lead to people gaming your system, and I think that we see that in a lot of things, like college admissions, applying a job application, you name it, the big decisions, most of them have been gamed to some degree or another.
Yeah.
And buying a house is huge, right? So it gives people a pretty big incentive to do whatever they can to get an advantage, where maybe like these less important decisions, people aren't really trying to game it. I'm not trying to game, like you mentioned earlier, like Google ads. Like, I don't really think much about which ads I'm being shown and try to search for certain things to get certain ads.
Yeah. But Zillow was a little bit unique, and it was actually very transparent in how it showed us its prediction. Like Google doesn't show you kind of your predictions as you go along. And really, I mean, I see all these things about like, I'm going to build like an adversarial hack against adversarial, like somebody's going to give me predictions and I'll build an adversarial machine that will take that down. But the reality is not a lot of algorithms and approaches out there actually share what the prediction score is that they get. Like, they're there and some people see it, but you don't actually get to see when you go to the hospital and there's a readmission score for if you're likely to be readmitted or not. Like the hospital doesn't tell you like, hey, here's our score. We really think you're likely to come back or not in that same way. So.
Yeah, I guess I was more thinking of ones where there's semi-open criteria.
Yeah.
Like in college admissions, we know some of the inputs because they've been so widely advertised. Like we may not know exactly what coefficients or modeling they're using, but we understand that they're going to take, GPA and, standardized test scores and whatever else could potentially be in it, and that people cheat in those or, game that system.
Well, no, I mean, so the U.S. News and World Reports has a formula for rating colleges, and they kind of tell you exactly how it is. And I can tell you because I saw the inside of faculties and stuff. Like the colleges spend a ton of money trying to game that system. So, for example, like if your graduates have a job after graduation, you're going to get bump up on the rankings. So this is what law schools will do: is literally hire the bottom of the class for the next 6 months, so that way they count as employed. And so that way they can boost up in the rankings. So yeah, I mean, everybody's always trying to kind of game these systems if they know, especially, and it makes it easier if the formula's out there for how to do it.
So do we have any other questions? Anybody? Okay, yeah, I guess that's good to go. Yeah, really, we definitely appreciate you coming by, and definitely reach out next time you have a project that you're willing to share. So
yeah, I always like hanging out with you guys. So yes, please feel free to reach out, and feel free to reach out individually to me as well if you have whether data science questions or on this topic. So no, thanks for having me.
Definitely. And for everybody, I think that Dan, you added the LinkedIn and the GitHub to the chat, correct? Okay, so yeah, so if anybody's interested in that, definitely follow us on LinkedIn and check out the GitHub repository.
All right.
But
Thanks, guys.
Good, thanks.
All right.
Thank you so
Good
much.
night.
Thank you all.
Thank you.
Thanks.